Let's talk about statistics. Let's talk about statistics and you. Welcome to the wonderful world of math with discrete random variables. Not just any random variables. Variables that know how to keep a secret. I'm just kidding. Discrete and discrete, not the same thing. So, a random variable is a variable whose values are numerical, and that's going to be kind of assumed, but that they depend on the outcomes of a random phenomenon or a probability experiment. So what does discrete mean? Discrete means that it has a finite or countably infinite number of possible values, a number of values that you can list, say in the column of a table. Discrete. Discrete as opposed to what? What else could it be? It could be continuous. Discrete versus continuous. Discrete. These are things that can be counted, things that are finite or countably infinite, like we said. Something like the number of kids, or how many fingers do you have? Continuous are things that can be measured. These are things that are an interval of values, like you could be 5 feet tall or 6 feet tall or anything in between. You could be 5.000012 feet tall. You could be 5.000013 feet tall, or anything in between those, right? All an infinite range of values just between 5 feet and 6 feet tall. There are so many that they are uncountably infinite that if you tried to put them in a list, you could not do it. There are too many. Things like height and weight, things that can be measured. Counted, measured. Discrete is what we're going to focus on now, things that can be put in a list. And for the purposes of this intro level, we're going to use finite rather than countably infinite. So for our first example, we're going to talk about European roulette, where there are 37 numbered slots on a wheel numbered 0 through 36. The 0 slot is green. The slots 1 through 36 are half red and half black. Here is a picture and the numbers and order they go from 0 to 32 to 15, etc. around in the clockwise fashion. Notice that there are three colors: green, red, and black. Notice that some of the black ones are odd and some of the black ones are even. Same for red. So there are three colors. We should be able to make a table listing the outcomes in terms of colors: red, green, and black, right? And we know the probability of getting red. The probability of getting a red one, there were, let's see, 1 through 36, half red. If you've got 36 things and half of them are red, then 18 of them are red. So 18 out of 37 slots altogether, including the green one. The black, same deal, right? 18 out of 37, and there was one green square out of 37. Now let's suppose that x, the variable, represents the amount of money I win on a bet. Let's say I bet $1. If it comes up red and I bet on red, then I get $1. If it comes up green and I bet on red, then I lose $1. If it comes up black and I bet on red, then I lose $1. Right? So these are different values of the variable for a bet on red. A numerical value that is based on the outcome of this experiment. For this particular one, you could notice that these are actually the same value of the variable, and we could turn this to red and not red, so that there's only two rows for the two different values of the variable, with a total of 19 outcomes that lead to not red. Right? So this is also valid. Well, let's say that I wanted to change my point of view, though. Let's say I want to bet on green. Let's say that I win $1 if it comes up green, and I lose $1 if it comes up red or black. In this case, there's still only two values of the variable, but they're assigned differently, so the probabilities are different. Green or not green. Green has a probability of 1/37th, and not green has a probability now of 36/37. It's again numerical values that depend on outcomes of my experiment, and they each have probabilities tied to them. The point of these examples is that the outcomes of the probability experiment may not be a quantitative variable. They could be a qualitative variable, like a color, right? But that we can still sometimes have a quantitative variable that depends on those outcomes. So x isn't necessarily the outcome of the probability experiment. It could just be a variable that is based on those outcomes, like in this red, green, black roulette scheme. So in general, we'll say that we have a probability distribution if we have a table that gives values of the random variable x and the corresponding probabilities, the probability that x equals a certain number. So here, in our previous example, we had the values of the variables 1 and -1, and the probability that x equals 1, the probability that x equals -1. And yes, most of the time, instead of writing p of big X equals little x, we just write p of little x, the probability that x equals little x. Every probability distribution must satisfy two properties: that the sum of all of the probabilities of all the values of the variable must equal 1, and that each individual probability must be between 0 and 1 inclusive. These are things that we needed to have for probabilities anyway, that the sum of all the probabilities of each individual outcome has to be 1, and that the probability itself has to be between 0 and 1. But now we're collecting it in sort of a different way. So if we have a probability distribution, notice that x isn't necessarily an outcome like we saw in the previous example. It could be a number based on outcomes. Probability distributions have to satisfy these two properties. If you ever made a relative frequency distribution table, congratulations, you have a pretty good idea how to do probability distribution tables. So now I want to do two things. I want us to practice making a discrete probability distribution, and I want us to look at a couple of tables and determine whether they are a discrete probability distribution or not, whether they satisfy the rules. So let's do one of those things. Let's take a look at this. A survey administered to 1,200 residents of Bananaopolis are asked how many pairs of Crazy Town brand banana pants they own. The results are given below in the table. Here we go. Let X represent the number of banana pants owned by a randomly selected 18 to 25-year-old, and let Y be the number of pairs of banana pants owned by a randomly selected 26 to 33-year-old respondent. Let's make a discrete probability distribution. So if we take somebody from this row, we've got a chance that a person belongs in this category, this category, this category, this category, or this one. What is the probability of one of these people being selected and landing in this category? Well, there's 36 people in this column out of how many people altogether in this row? We need totals. If you add these up, you should find that the total is 600. Try to find the total of the second row. 600. That way it adds up to 1,200. Yeah? Nice. Great. So the possible values for this x were 0, we had 1, we had 2, we had 3, and we had 4, right? Those are the possible values for our variable, and we saw that there were 36 out of 600 ways to be randomly selected as somebody who owns 0 banana pants in this age range. And we can go ahead and make this into a decimal, because that's what we usually do for this stuff, right? Although you'll find that sometimes fractions are going to make this easier rather than decimals. What's the chance that a randomly selected respondent in this age range, 18 to 25, is going to fit into the one pair of Crazy Town banana pants? Well, there were 140 people in this column out of a total of 600 people. So 140 out of 600 as a decimal, that's a 23.33% chance. Now, go ahead and do the other three possible values. P of 2, P of 3, P of 4. Let's check in 3, 2, 1, and... Okay, and you'll notice that this one and this one had to get rounded. The other ones were exact, but these ones had to get rounded. You should check that this satisfies the rules that all of these things add up to 1. If you're going to write it with decimals, you better make sure that it still adds up to 1 and satisfies the rules. Yikes. Okay? So, that's why I prefer the fractions, because no rounding means it should add up to what it's supposed to. So now what I'd like you to do is I'd like you to make a table for y. These are going to be different probabilities, right? So we still have the same 0, 1, 2, 4, and 3. but they're going to have different probabilities. Go ahead and find them. Are we ready? That, by the way, was the sound of our probabilities missiles launching and landing and exploding into a rainbow of color. This, then, is the probabilities that a randomly selected respondent aged 26 to 33 is going to have this many pairs of banana pants. Notice that we rounded everything to 4 decimal places if we had to round it, like we always want for probabilities. If you've said to yourself over the last couple minutes that, Professor Acer, isn't this exactly how we do relative frequency tables distributions? And the answer is yes. Yes, it is. So, the perspective is what's different here. The following are examples of things that may or may not be discrete probability distributions. Let's look at this one first. We've got values of variables and we've got probabilities, and they actually kind of look like the probabilities in the last table, right? Do they satisfy the two properties? That is, are each of these probabilities numbers between 0 and 1 inclusive? That means they could be 0, could be 1. Yes, none of them are negative. Nobody's below 0. Nobody's bigger than 1. It just all starts with 0 point something. Great, great. Now, is the sum of all of this equal to 1? Why don't you go ahead and check? Pause this and add them. 5, 4, 3, 2, 1. All right, and you should get that this is 1 point, not 0. 1.0001. So this is not a discrete probability distribution. In case you were wondering, it does look like the previous example, but not exactly the same, because I tried to do it when the numbers were slightly different, and rounding made it not add up. This is just a rounding error, and generally we'll kind of overlook this stuff. How about this monstrosity? Is this a discrete probability distribution? No, of course not. Why not? Two conditions. That each of these numbers has to be between 0 and 1. It is. None of these numbers are negative. I don't care that this is negative. That's fine. These can't be negative. They can't be bigger than 1. These are all fine. The problem is that when you add them up, you get quarter plus a quarter plus a quarter. That's 75 cents, right? 3 quarters plus 3 dimes. This does not add up to 1. So, again, we violated the first one. This is a little bit more than just a small rounding error. There's something missing or something wrong with this. How about this one? Again, these are all satisfactory individually, but as a group, the second property is violated again because you're not going to add up to 1. The sum of these probabilities is going to be 0.44. So that's a big no. How about this one? Why isn't this a discrete probability distribution? Well, first of all, these definitely don't add up to 1. They add up to 37, and they're way bigger than 1 to start with. We need the probability of getting 1,000 to be between 0 and 1. It super isn't. We also need this probability, the probability of 25, well, negative 25, to be between 0 and 1, and it also isn't. We also need the sum of the probabilities to be equal to 1, except that they're not, because the sum of the probabilities, again, 37. So none of these conditions hold for this. So if I ask you if something is a discrete probability distribution, discrete means that you can count them in like the rows of a table, you can list them. But the probability distribution means that it satisfies these rules, that each individual probability has to be a probability between 0 and 1, and that the sum must add up to 1. Now the next thing we want to do is talk about a probability histogram, which is a lot like a relative frequency histogram. In the same way a probability distribution is a lot like a relative frequency distribution. And to do that, we're going to get a new example that's easy enough for us to draw a bar graph, a histogram for. A coin flip is flipped, a coin is flipped 4 times. The number of tails is recorded. If you haven't ever done this before, you should probably figure it out at least once. I recommend trying to use a tree diagram. If you don't know what that is, look it up. I made a video for it. On each branch, you make a decision. We're flipping a coin 4 times, so we make 4 decisions. Each time, there's only 2 choices. It gets kind of big, though. So make your tree diagram, and when you come back, in 5, 4, 3, 2, 1, you should get this. These are the outcomes, the sample space of flipping a coin 4 times. How many tails does each of these have? So we go ahead and we count the number of tails in each outcome. And then what we're going to do is we're going to figure out how many of these have 2 tails out of how many altogether. How many outcomes are there altogether? 16. 16. So how many times do we get 2? 1, 2, 3, 4, 5, 6. 6 out of 16. How many times do we get 0? Once. How many times do we get 4? Right? We got to make sure that this adds up to 16. There was one way to get this. There was one way to get this. Counting up the ones should be a little easier. 1, 2, 3, 4. 4 ways to get 1. 4 out of 16, which of course reduces to 1/4. 3. Let's count up the number of 3's. 1, 2, 3, 4. That was easy. So 4 out of 16, which also reduces to 1/4. 1 plus 4 plus 4 plus 1, that's 5 plus 5, that's 10. 10, leaving us with 6 left over, which is exactly what we counted for the 2's, making sure that we did this right. This reduces to 3/8. And this is a probability distribution. What we wanted for this was to be able to graph this. So again, here's our probability distribution table, and we're going to graph this. Now, probability histogram is a graph where we've got one vertical bar for each value of x. The heights of these bars are determined by the probability for getting that value of x. Other things about histograms in general is that the bars are equally spaced, that is, they're all the same width, and that the bars are touching. So according to the previous problem, if we want to make a probability histogram for the number of tails in 4 coin flips, we're going to have 0 tails 6.25% of the time. So right about there, a little bit higher than 0.5. And now for 1 tails, we're going to have, that was 1/4 of the time. So and already you can see that my bars weren't equally spaced, so I fixed it. Oops, fixed. Great. For 2 tails, that was going to be 37.5%. So that's above the vertical axis I could fit under the description. And then we're back down to 0.25 or 25% for 3 tails, and then a nice 6.25% for the last one. This is a discrete probability histogram. Any questions? Not like I could answer them, but maybe write them down, ask me later. Okay? Can you make a discrete probability histogram for this problem with the Crazy Town Banana Pants? Try it. Alright, are you ready with that histogram? I gave you lots of time, although I paused it. You should have paused it. That was your chance. Second chance, going once, twice, 3 times a lady. This is what our discrete probability histogram should look like for X pairs of banana pants owned by a randomly selected 18 to 25-year-old from our survey. That's it. That's our stuff. So our constellation for the day is Columba, the dove. And this has been a Badger Bear production of the Wonderful World of Math.